Hey folks, this is Horner, and we're going to look at number 1 through number 5 for constant velocity motion problems. The first one talks about the young person that was dropped off with a Razor scooter at Westfield Middle School, and they're going to travel over to Westfield High School. And this person's name is Ion. The position that this person starts at is 20 meters from the front door of the middle school. So we're going to say that the original position, so XO, here is equal to 20 meters, and the final position, or XF, is equal to 825 meters. It says that it takes the amount of time to go from position XO to position XF, which is from Westfield Middle School to Westfield High School, is about 240 seconds. They want to know what is Ion's average velocity. We know that average velocity is equal to XF minus XO, so that's the change in position, all divided by the time. Let's go ahead and plug everything in. We have 825 meters. Remember, you don't need the units here, minus 20 meters, and we can divide that by 240 seconds. So on the test, remember, this is a point. Plugging everything into the equation is a point. And then finally we need a number and we need a unit. So we're going to take 825 minus 20, and then we're going to divide that by 240, and we end up with a speed of a velocity of 3.35 meters per second. And that is the end of number 1. So let's go ahead and go on to number 2. Number 2, it's the same problem, but this time they want to know what is Ion's average speed. And for this one, we need to use a slightly different equation. Remember, v without the line on top is going to be speed for us, and that is distance, not displacement, but distance divided by the time that it's elapsed. Because he now has to go a longer distance, since he can't just cut through the grass and go from point A to point B, we know that his distance is 930 meters. The trip time is about 240 seconds. So once again, we have our two things that we need in order to do these problems. I'm going to take 930 and divide it by 240, and we end up with a speed here of about 3.88 meters per second. And that's a lot bigger. Well, relatively speaking, it's a little bit bigger than the one that we just did for average velocity, and it's because typically with distance, when you follow the whole path, it's longer. It doesn't always have to be, but typically that path is longer. Next problem, we're talking about Jamaica here. She's driving her car to her friend's house on the other side of town. She has to park about negative 20 meters from her house. So that is going to be our original position. So that's negative 20 meters. She goes by her house, which is at position 0. So if you kind of think about this, here is her house. And there's a little door for her house, and we'll put a little roof on here. It's a really great picture. She parks at negative 20. Her house is at 0, and then we're looking for whoever lives over in this area, and that is her friend. Let's go back. We don't know what XF is. That's what we're looking for. So that's our unknown. She drives for a good time of about 800 seconds. And her average velocity is about 20 meters per second. So they want to know at what position is her friend's house. Let's go ahead and set this one up. We know that the average speed is equal to XF, that's what we're looking for, minus XO, all divided by our time. So let's plug everything in just the way it stands. You could also, if you wanted to, solve this for XF, minus XO, and that will be equal to your average velocity times time, and then your final position then comes out to V times T, and then we have plus XO. So that's the equation that we're pretty much used to when we do our graphs. You could also solve it using this equation. Let's go the easier route and use this one. The final position that we're looking for is equal to the average speed times the time of 800 seconds plus our XO, and realize that this one is negative 20. So here our XO is negative 20. So let's find out what our final position would be. Here we've got XF is equal to, we take 800 times 20, and you should end up with 16,000. So go ahead and plug that in. Minus 20. And if I take 16,000 and I subtract 20, I should end up with the right answer. And that answer is 15,980 meters. So that is the position here. It's 15,980 meters. This is negative 20 meters. So notice that her entire distance that she traveled was from the negative 20 to the 0 and then to the 15,980. And so that total distance would be about 1,600 meters. So you see that right here. For the next problem is number 4, and it says in number 4 that while building the tunnel under the French Channel, déjà vu, get it, déjà vu, it's French, the drill operator moves at a pace of, so here we're looking at a velocity, 1.23 meters per second, and the time that we have here is equal to 3,623 seconds. They want to know what is the displacement. So remember, displacement is XF minus XO. The other way you could write that is delta X, because remember that's just the change in the position of that object. And I know it does say at the end of the day he only worked for 3,623 seconds and got paid for a full day, so we can just assume that. Let's go ahead and plug everything in. So we have XF minus XO, or delta X, either way you want to do it. We know that that's equal to your velocity, average velocity, times time. That came from our equation. Remember, V is equal to XF minus XO all over T. So all I do is just take the T, multiply it by both sides, and I end up with the equation that you see here. Now I can go ahead and plug everything else in. We know our velocity is 1.23 meters per second, and we know that our time is 3,623 seconds. If I take 1.23 and multiply it times 3623, I end up with my answer. That answer is about 4,456.29, and our unit here, because we're looking for how far he went, we wanted to know his displacement, and that would be in meters. Our last problem that we're going to do in this set is number 5, and during the Apollo moon landing they did place some reflecting panels on the moon. So people that are on Earth, so here's Earth, here's the moon over here, could shoot a laser over to the moon. That laser light would then hit the moon and come back, and doing some math using the speed of light and using the time it took to take that trip, they could figure out how far the Earth was from the moon very precisely. The speed that we're dealing with here, the velocity, is the speed of light, which is 3 times 10 to the 8th meters per second. We're going to go ahead and put average velocity on this, and we have to be very careful because the total time for the round trip is equal to 2.52 seconds. So let's go ahead and solve this, and we need to do something so we only get just 1/2 of this entire trip, because we really just want the distance between the two. We know that speed, or velocity, is equal to change in position all over our time, and if we really want to know what the distance was, we just say that the change in position, which is distance, is equal to the average speed times time. Speed of light is 3 times 10 to the 8th, and then we're going to multiply that times the time, which is 2.52 seconds. If we multiply 3 times 10 to the 8th times 2.52 seconds, we end up with 7.56 times 10 to the 8th meters. Now that would be for the entire trip. That would go starting at the Earth, come all the way to the moon, and then be shot all the way back. We only want half of this. So to fix this number so that it's actually what we want, we need to divide it by 2. We're going to take 7.56 times 10 to the 8th and divide that by 2, and you end up with 3.78 times 10 to the 8th meters. And that is a better answer than what we had before, because that is actually the distance then from the Earth out to the Moon. And that is number 5, and that's where we'll stop, going to number 6 through 10 in the next video.